All right, this is the video for Chapter 6, TI-89 Calculator Tutorial, and I am starting on Chapter 6, Worksheet 1, which we did back in the day. And you could certainly do this first problem without any fancy tricks, just, basic calculator functions, but there is a little shortcut I want to share with you. So this would be for problems where you have a table that shows the possible outcomes of a discrete quantitative variable along with their probabilities, and we want to find the mean variance standard deviation. So those formulas are pretty easy. They're just a bit tedious, right? You can see my work here of taking each outcome for y, multiplying it by its own probability, adding those together. And this is, 5 terms. If I have even more than that, it gets more annoying. And then don't even get me started on the variance formula where you're finding deviation squared for each outcome times probabilities. Now, don't get me wrong, you still need to show work for this stuff on an AP exam and on a test, but there is a way to get the numerical answers actually really quickly. You can at least use to check your answers. So what I'm going to do here, get my calculator popping, and I'm in my stats list editor. What I've done is I've taken all the possible values of this variable y, number of broken eggs, 0 through 4, and I have inputted those in the first list in the stats app. And then in list 2, I've put in the corresponding probabilities as documented on the worksheet. And what I can actually do to get the calculator to correlate these in the way that I want is I can go to F4, one variable stats, as we've seen in a previous video. And I can say, hey, calculator, I want to find the average of my variable that's in list 1, but I'd like the frequency of each result to be indicated in list 2. So that's what we use this frequency cell for in some cases. So list 1, outcomes, list 2, probabilities goes in frequency. And now when you hit enter and wait for a moment, we do get 0.56 as the average, the weighted average, which matches our answer down in part C. Scrolling down a bit, population standard deviation 0.898 does match our eventual standard deviation in part E. Now, I don't believe it gives us variance in here. So, actually, what's this? Well, it looks like it does actually give you the variance, the sum of deviation squared 0.8064, although you could have also just squared your standard deviation. And again, you still have to show some setup work to prove that you know how to do this without a calculator. But there's a shortcut for checking your answers. All right, so that's the first of 3 things that I'm going to cover in this Chapter 6 video. And for the next, we're going to make our way over to Chapter 6, Worksheet 3, which I've got somewhere here. There we go. And Chapter 6, Worksheet 3, we looked at binomial and geometric distributions. These are a couple more concepts where you have some work you need to show to demonstrate that you know some formulas, but there are calculator shortcuts for the computation. So you can see, I'll just stick with problem number 1 here. Binomial situation is where we have a fixed number of trials. Probability of success is the same in every trial. What are the other conditions for that? There's only 2 possible outcomes, which we consider success and failure. So in this situation, it looks like the probability of being admitted to the hospital is always, what is it? 0.27 there, it took me a second. We have an answer. Let's see if we can get the calculator to do it for us. So again, I'm going to be in the stats app here. And let's exit out of one variable stats, and we're going to make our way to F5 distributions. We've already learned about inverse normal, normal CDF. You can see T and chi-square. Eventually, those will be covered in a video as well. But if you scroll down near the bottom, you got your binomial, and you've got a geometric options as well. So we're going to go with binomial. And you could actually use either of the binomial options for this particular problem. Eventually CDF is the more powerful one that'll do all the problems, but I'll use this one to show PDF. Binomial PDF wants you to first input a number of trials. Well, for us in this problem, we have, looks like 40 80-year-olds that we're measuring. So each one is like a trial. Probability of success is 0.27. And then for X value, it's wanting you to input the number of successes that you're investigating. So what's the probability I get exactly 10 successes? I would put in a 10 here. Hit enter, wait for a moment. 0.1385 is the answer we get back. And that is in fact the answer we get using the conventional formula as well. Yes, you still need to show this work that I'm hovering over here. So this doesn't excuse you from showing work, but it is a way to check your answer. Now, once I exit out of that, I'm going to show you binomial CDF. This is actually more powerful because it allows you to input not just a single number of successes, but a range of possible successes. So number of trials, I'm going to stick with 40. Probability of success is still 0.27. Lower and upper value. So this would be useful for the second part of the problem where it says, what's the probability that we get between 10 and 15 80-year-olds admitted to the hospital? So that's giving you an upper and lower bound. Lower is 10, upper is 15. So go ahead and hit enter, possibly twice. 0.619, 0.619, answers match up. Okay, so CDF is, I guess, better. Now, you could even use CDF to answer the first question that we already did. Oops, wrong CDF. I need binomial. What am I doing? If I want to set this up to do exactly one value, I could have just said the number 10 for both upper and lower, and that's going to give us the same answer that we had previously for the first part. So if you're going to only know one of those, the CDF is the better one to know. All right. From there, I'm going to now scroll down to the third and final trick featured in this video. I'm scrolling down to the bottom because the last page has some geometric distributions. I like number 10 because it's got a dog. And again, geometric, this is where we don't have a fixed number of trials. Instead, we're finding a probability of the first success happening on any particular number of trials. Like, do I get my first success on the third attempt at something? What's the chance of that happening? Do I get my first success on the 12th attempt? What's the chance of that happening? You've got formulas and work you still need to know how to show, but we also now have a calculator trick to help get the answer. And you can find it, F5. Instead of scrolling down, it's better to scroll up since geometric is at the very bottom. There's a PDF and a CDF. So for question 10, the first part, what's the probability it takes exactly 2 tosses to get a success? I could go with the PDF version. All I need is the probability of success. It looks like it is 0.1 for the dog. And my X value is going to be the number of trials. Here it says, what's the chance it takes 2 trials, 2 tosses? So I'll put in a 2 there. I should get back 0.09, and I do. What's the probability that more than 3 tosses are required? So this is cumulative. It's not looking at just a single possible number of trials. It's 3 or more. It could be 3, or I'm sorry, it couldn't be 3. It's got to be more than 3. So it could be 4 or 5 or 6 or so on. So I'm going to try CDF, but we have a little bit of a problem here because for reasons I don't really understand, you might recall with normal distributions, we could use infinity for an endless upper bound, but it doesn't let you do that for this geometric feature. I don't know why they programmed it this way. In fact, I'll even try it to prove it, but probability of success is 0.1. If I want more than 3 tosses, well, I have to be careful because these lower and upper values are inclusive. So if I put a 3 here, that's wrong because then it's going to try and include 3 as an option. I need this to be more than 3. So I'm going to start it at 4. I'm pretty sure this isn't going to work, but I'm going to try infinity just to prove that it doesn't work. Domain error. Okay, so what do we do instead? If I leave this thing blank, I think we're still going to get a domain error, argument error. Well, you got some options, okay? You could just type in a really, really large number because the amount of probability that you're changing as you add on case after case and case, it's like diminishing returns. So if I put in, like, let's say 1,000, this should give me close enough to the right answer that we're fine. So yeah, there it is, 0.729, 0.729. But the other option is I could set up my geometric CDF to have a lower value of 1 success, an upper value of 3 successes. Those are actually the cases I don't want. I could go ahead and run that. I get back a 0.271, and then I just have to know to subtract my answer from 1. So I think it's probably quickest and easiest if you just decide to put in a really, really large number as your upper bound, if you mean for it to go to infinity. But yeah, that's a couple options on how you could do it there. All right, I believe that's it for chapter 6, new calculator tricks. As always, give me a holler if you have any questions. Stay tuned for videos for the second half of the course coming soon.